whole process takes about 30 seconds. So for the moon to cover the sun and then come back off it all the way would take 1 minute at that rate. And I'm assuming that this is happening in real time and Kenshin's not standing there for 2 hours, which is the amount of time it should actually take. So in other words, the anime moon is moving 120 times faster around in orbit than our moon really should. The problem with that is that when you have things that have mass and having a speed, they tend to kind of just want to keep going where they're going. This is called momentum. And so to keep that moon in orbit, there's going to have to be a larger force keeping it in orbit, and that force is going to be gravity. So the question I want to look at with this is how much more force, gravitational force, are we going to need to keep that speedy little moon in orbit? So that's how we're going to look at it first. Getting some numbers to work with, the real orbital period of the moon is about 30 days, slightly shorter. Putting that into other units just so we can work with them, the important one here is it's about 2.5 million seconds. Anime moon 120 times faster, so we get it does that whole orbit in about fourth of a day. Pretty quick. Other things we need to worry about is we're going to need some masses here. The mass of our Earth is about 6 times 10 to the 24th kilograms. If you're not good with scientific notation, the number on the 10 tells me how many times to move the decimal places to the right. So that's going to be a 597 followed by 22 zeros. That's a pretty big number. The mass of our moon is 7.36 times 10 to the 22 kilograms, and the distance to moon, and I'm using perihelion here. Perihelion means the closest point, because its orbit isn't perfectly circular on us. It's sometimes further, sometimes closer, but when it's the closest, it's moving the fastest. So I'm trying to give it the benefit of the doubt here. So that's where it's going to move the fastest. And what we need to do is we need to look at Newton's revisions to Kepler's third law, because it happens to relate all this stuff. It has the funny looking T off here to the right side. That's the period, so how long it makes the full orbit. It's got 4, it's got the pi, it's got a cubed. A cubed is the semi-major axis, or basically the distance to the moon. And g is the gravitational constant. You have the mass of one body and then the mass of the other. What we wanted to know again is what is the mass of the Earth going to be. So we have the mass of the Earth, mass of the moon, and since we have almost all this information, we can go ahead and solve this. And that's what I do here. So we solve all that, just algebra, rearrange it, solving that for the masses. Now we could actually do a couple different things here. We could change the mass of the moon, make it a lot heavier, which would make it orbit faster. But if we make it too big, then it's going to orbit, or we are going to orbit it, and it won't orbit us. So I'm going to have to leave that one constant. Another thing we could do is we could change how far away it is. If it's closer in, it'll move faster. But then the sizes would be wrong, and it wouldn't just cover the sun, it would cover the whole sky. Can't mess with that one. I could mess with gravity, like the gravitational constant, but then like the whole universe would fly apart. I don't want to do that. So the only variable that I'm going to really be able to leave variable here is the mass of the Earth. And so when you plug all that in, you get that the Earth, instead of weighing that 10 to the 25th kilograms, should be 10 to the 33rd kilograms. In other words, we can ask, what is the surface gravity going to be? We know on Earth, we get pulled down at a rate of 9.8 meters per second squared. That's the acceleration that gravity's always pulling on us. But if we look at that for this new one, what the surface gravity would be, and this is the equation to figure that out, we get that the surface gravity is going to, instead of 9.8 meters per second, is going to be 2 times 10 to the 12th meters per second squared. So roughly 2 followed by 12 zeros. No one's laughing at this. Which tells me we're still having trouble understanding the scientific notation of math, which is good because I said I'd explain it. It means you would weigh 220 billion times as much. Even a skinny white boy like me is worried about that one. So there is no way that the anime moon could possibly work. Same thing in Heroes. You're not going to sit there and watch a full solar eclipse. They do have big parties that just go out on boats and go to remote locations to watch these. But they're like day-long events, and it's all sorts of fun. I've always wanted to go on one. But having it happen in a full minute, not realistic. So let's look at another topic. This one's from my favorite anime, Gurren Lagann. And at the end of that series, so they have a planet, they zoom out, show the solar system, zoom out more, hey, look, all sorts of solar systems, zoom, oh my gosh, it's a whole bunch of galaxies. What's inside? A giant freaking mech that's like walking around on galaxies. My question is, Mr. Owl, how many galaxies are you going to have to cannibalize to build that thing? So we can start off, it's about 1/10 the size of a full galaxy going across there if you count it up. So what I want to do is I want to take something that I know how much stuff there is in it and scale it up to be that size. So I'm going to start with the car. I figure it has about the same roughly amount of weight with the metal in it and then the blank space in between where people sit or walk around in corridors in the mech. So I'm going to use a car. Length of a car is about 5 meters, but meters are not going to be a good unit to use when we're talking scales of galaxies. So I convert that to light years and we get 5.3 times 10 to the 16th light years. I'm sorry, negative 16th, which means cars are very small compared to galaxies, let's put it that way. Meanwhile, a real galaxy is huge. It's 100,000 light years across, which means if we want to get a conversion factor that says how many times are we going to need to scale it up just in the length, well, we can divide that out, and we get that the galaxy is 2 times 10 to the 20th times bigger than a car. Repeating that for the height and the width, we get that the galaxy is going to be 1.3 times 10 to the 19th times the height, and 6.3 times 10 to the 20th times the width. So I've kind of built now height, length, width, and if I put that all together to get kind of a three-dimensional box, a galaxy overall is 2.1 times 10 to the 58th times bigger than a car. So let's worry about what the mass is going to be. A car has about 770 grams of steel, but steel isn't a naturally occurring element. That's something we make. Most of that is black and disappearing. There we go. 95% iron. So if I multiply that out, that means a car is going to have about 730 kilograms of iron, which we then multiply by that little scale-up factor, by little I mean big, which means we're going to need 1.5 times 10 to the 61 kilograms of iron. All right, big number. Again, let's try to figure out what that's going to be in context. Is what's a galaxy? Of paltry 1.9 times 10 to the 43rd kilograms for the weight of the whole galaxy. In other words, we need 7.9 times 10 to the 17th galaxies just to make up the same mass. So that's about 8 times 10, so 80 billion galaxies. And notice I underlined mass here, because there's one more problem, and I'll get to it in a second. Everyone recognize this guy, Hubble telescope? All right. Back in 1909, it did this really crazy thing. It looked at the blankest region of the sky they could find. It's like there's nothing here, and some astronomers, they did their study, and they had some extra time on the telescope, so they go, let's just stare at an empty spot in the sky and see what happens. The spot in the sky is about the size of Roosevelt's eye on a dime, held at arm's length. It's tiny. But they just stared and let all the light collect on the camera, and just collect. And what they got was this. They got this picture of faint things that they didn't know were there. And every single thing in that picture is an entire galaxy at the edge of the observable universe. Way, way, way distant. But what they did is they said, okay, well, if we got this many galaxies, and they counted them all up in the picture, and that's for a stretch of sky that big, well, how many would it take to cover the whole sky? So they multiplied it out, and they got this estimate that there should be 1.25 times 10 to the 11th galaxies in the entire universe. So what was that compared to what we just said? We need 6.3 times 10 to the 6th, or 6.3 million universes to make up the same mass. I did my BS in astronomy. I've worked with the biggest universes or units there are, but I'd never worked with universes until I tried this. You can't get bigger units. So that's kind of crazy, but there's still, as I said, one more problem, is that galaxies aren't made of nothing but iron. Galaxies are only made of about 0.0001% iron. It's tiny. Most galaxies are about 75% hydrogen, 23% helium, 2% everything else. So 2%, and only a tiny fraction of that is iron, which means we're going to have to cannibalize a lot of galaxies just picking out the iron to do that. So we need to multiply that by our previous result, which means we need 6 1/3 billion universes to make that mech. Now for those of you that have seen the series The bad guy was actually kind of this weird good guy because they were trying to prevent the Spiral Warriors, the main characters, from using the spiral energy in the universe would eventually go out of control and destroy the universe. I think they have a lot more to be worried about than that one universe, apparently. They will go around destroying billions of universes just to make a mech. So now you know who the real bad guys are. But there is one way we can save this. And that also comes from that same episode, because when they defeat the bad guys, the whole galaxy suddenly blows up.
Wow.
3 times, in fact. Good measure. The problem with that is you can't get things exploding that fast. There's this whole funny thing called relativity, which means that there's a speed limit of how fast things can go. And that speed limit is the speed of light. So this galaxy blew up in 9 frames. And at 30 frames a second, that means it went in 0.3 seconds. So the galaxy from the very center all the way out to the edge, just in 0.3 seconds. Unless they were doing like Kenshin and just standing there for eons. So I'm going to assume that this was real time again. But you can't have it actually happen that fast, because that explosion can only be carried along at the speed of light. And if you want to be really strict about it, it's actually not going to be the speed of light, it's going to be the speed of sound. But I'm going to give it the best benefit of the doubt here, say, sure, we'll carry it at the speed of light. The thing is that you multiply that amount of time by the speed of light to figure out how large that galaxy actually was. So you do that, and it's only about 90 million meters across, compared to 100,000 light years. I mean, not even comparing here. Putting that in context again, what this means is that this galaxy that they're walking around on is 5 times 10 to the 12th times smaller than what I was just using in my previous example. In other words, that whole galaxy was only about 4 times the distance to the moon, which kind of just unepicked Gurren Lagann.
So, you need less iron.
You need a heck of a lot less iron, and it actually makes it still stupid, but feasible. So, that one actually could potentially work if you wanted to cannibalize like 90% of one universe. I still wouldn't appreciate it very much. All right, let's take a look at another one. Those were ones that I had done in 2009, 2010. These are the ones that I developed for 2011, and they're all about the Pokemans. So, first, Macargo. According to the Sapphire Pokedex, he's one hot mother. It says his body temperature is 18,000 degrees Fahrenheit. Yay, decontextualized numbers. Let's contextualize that. First, look at some other units. About 10,000 Celsius, or if you prefer absolute 0 scales with Kelvin, a little over. That's about twice the temperature of the surface of the sun. Okay, well, what's so bad about that? Well, the sun causes sunburns because it gives off quite a bit of UV. So how much sunburn are you going to get if you capture that Pokemon just like standing 10 meters away? So that's what I wanted to know.
But it's inside of a shell.
The problem is that you can't keep things contained. There's no such thing as a perfect insulator. So eventually, that heat internally is going to spread to the shell, and then the shell will equalize. It will be the same darn temperature. So, yeah, if you just magically poofed a Macargo into existence with a nice cool shell, it would probably last a couple seconds if it weren't truly vaporized, but this is anime. I'm giving it the benefit of the doubt. So yeah, let's talk about how much UV you would get from a Macargo at 10 meters. The first thing you have to understand is that things give off light in a lot of different colors. We can only see this portion down here, which is the visible part. But there's all sorts of other portions of light that we can't see with the human eye. Off to the left side on this graph, they have the ultraviolet, and then past that is X-rays, gamma rays, and off to the right side you have the infrared, the radio, and things like that. What we're really interested in is the ones just past the blue on this graph, because that's the ultraviolet. That's what's going to give you the sunburn. And the amount of area underneath these kind of curves is going to tell you just how much ultraviolet you're going to get. The other thing to notice is that there's several different little charts on here, and every single one of them is a different temperature. So this first one down here is 3,000 degrees, and then 4,000 degrees Kelvin, 5,000, 6,000. And what you see is very quickly, they're getting much bigger So that means more area underneath, which means more ultraviolet. And then also,